Gauss theorem. So it states that the angle which says that the angles in the same segment are congruent or equal. So the theorem states that the angles in the same segment are equal. So assuming if you have a circle, so if you have theta 1, we have theta 2. So the theorem states that theta 1 equals theta 2. You can even state it as the angle, the inscribed angle. The inscribed angles of the same intersected arc are congruent. If you notice, they have the common intersected arc, so they are equal. So see the quick proof. It's very easy to prove. I can prove it direct. Assuming this is the center. This is the center. This is the center O. So this is my radius. Sorry. So if this is the radius R, from inscribed angle theorem, you notice that we have the central angle. Let's call it beta. So our central angle, let me go A, B, C, D. So you notice that angle AOB is equal to 2 theta 1 by inscribed angle theorem. Inscribed angle theorem. Okay. Also, that same angle AOB is also 2 theta 2. The same reason. So this angle AOB, that same angle AOB, so which implies that 2 theta 1 equals 2 theta 2. Therefore, theta 1 equals theta 2. So that's the theorem. So once you have two inscribed angles with the same intersected arc, they are always congruent. They are always equal. So the next theorem is cyclic quadrilateral. Okay, you'll be wondering, what is a cyclic quadrilateral? A cyclic quadrilateral is just a quadrilateral that is inscribed in a circle. So if you have a circle, and you have a quadrilateral, so this is quadrilateral A, B, C, D. So if all the vertices of the quadrilateral we call it a cyclic quadrilateral. So there is a special theorem for that. So it states that the opposite angle of a cyclic quadrilateral are supplementary. So I'm saying that if you have theta 1 here, and we have theta 2 here, you have beta 1 here, you have beta 2. The theorem states that the sum of the opposite angles of a cyclic quadrilateral are supplementary. So the theorem states that the sum, that's theta 1, beta 1 plus beta 2, must be equal to 180 degrees. And theta 1 plus theta 2 must be equal to 180. That's what the theorem states. So we can see a quick proof to that. So there's a quick proof to that. So if you have a quadrilateral, okay, if you have so this is a quadrilateral, that is a cyclic quadrilateral, A, B, C, D. So from here, if here is the center of the circle and this is the radius, so if here is theta 1 and here is theta 2, so you notice that angle B OC, that's I'm saying that here B OC, I'm saying that this angle is 2 theta 1. Why here is 2 theta 2? You know why? Based on inscribed angle theory. So from here we have angle at a point. So if you add 2 theta 1 plus 2 theta 2, must give us 360 degrees. That's angle at a point. So we factor common term, which is 2, equals 360, which implies that theta 1 plus theta 2 is 360 over 2, which is 180. So that's what the theorem states, that if you add the opposite angle of a cyclic quadrilateral, it must be supplementary. There's one extra theorem for cyclic quadrilateral. You notice that if here is theta 1, here is also theta 1, because since theta 1 plus theta 2 is 180, this is a straight line, so here should be theta 1, because if you add the 2 again, the answer is 180. So whenever you extend the exterior, you extend one of the sides, the exterior angle form is always equal to the opposite interior angle. So whatever that is, the same way, if you extend this, whatever should be here should be B2. So we need to remember this. It's also helpful. So see a quick example to that. If you have a circle, you have a circle. So let's with the quadrilateral ABC inscribed in it. If here is x plus 10, y here is 2x plus 20, we are asked to find the value of x. So without wasting time, the answer is simple. So looking at this is a cyclic quadrilateral because the vertices of the quadrilateral are on the circumference of a circle. So we have that x plus 10 plus 2x plus 20 must be equal to 180. That's it. So we add x plus y is this, so opposite angle of a cyclic quadrilateral. So we add x plus 2x is 3x. So 3x plus 10 plus 20, 30 equals 180. So as you can see, 3 is common. So we can divide each by 3. So finally, x is 50. 60 minus 10 is 50. So x must be 50. So that is a quick example to illustrate that. So the next theorem is the alternate segments or tangent cut theorem. The theorem is, so we have alternate segments, or you call it tangent chord theorem. So the theorem, from the name tangent chord, has something to do with a tangent line and a chord. So the theorem states that if you have a circle, and you have a tangent to the circle, so this is a tangent line. So if you have a triangle this way, a triangle, let's call it A, B, C, a triangle such that the one of the vertex is also at the point of tangency of the circle and the tangent line. So the three of them meet at a common point. So if you have theta 1 here, so it's always equal to theta 2. So the theorem states that, or if you have beta 1, is always equal to beta 2. So the theorem said that theta 1 must be equal to theta 2 and beta 1 must be equal to beta 2. So that's what the theorem states. So if you have a circle and a triangle is inscribed in such a way that one of the vertices is also has a common point with the circle and the tangent line, so the angle forms in this way, they're always equal. So maybe let me show you a quick proof to that. So if you have it, this is my circle. So this is my tangent line. Sorry. If you have a circle, So if you have a tangent line in this way, and if this is the center of the circle, we have a radius drawn to this point. So, and so we have a line trying to draw a triangle. So if you have a triangle inscribed in such a way, in this manner, say let's call this A, B, and C. Assuming here is the center of the circle. So you know this is the radius. So this is my radius, and it's always 90 degrees to the tangent line. This is the tangent line. So again, this is also the radius of the circle. So remember, assuming here is theta 1. Our main aim, this is theta 2. So you notice that the angle here is 90. The angle here is 90 minus theta 2. So, and also here, 90 minus theta 2, because it's an isosceles triangle. So looking at the central angle, so you notice that, which implies that angle COB will have two values. So it's either is 2 theta 1 based on inscribed angle theorem, or is also equal to 180 minus the sum of the remaining, the sum of the other two angles, which is 90 minus theta 2 times 2, because they are the same. 90 minus theta 2, 90 minus isosceles triangle, so it's 2. So this is based on angle sum theorem for triangle. So that's the two values. So which therefore 2 theta 1 must be equal to 180 minus 2 times 2 times 90. Two times 90 minus theta 2. So opening the bracket, this is 180 minus 180 plus 2 theta 2. Like this, 2 theta 1, 180 minus 180 is 0, so 2 theta 2. Therefore, theta 1 equals theta 2. So we'll prove that angle in alternate segment theorem. We've proved the alternate segment theory, so we'll stop here. Let's go to the main thing, which is exam to solve questions, technical questions using these theorems. Thank you.